To understand the fundamental relationship between position, change, and rotation, we can look at the transition from simple linear movement to the complex swirl of angular momentum. This derivation sheet explores how mathematical identities describe the physical world through symmetry and visual flow. At its simplest level, we can visualize a physical field, such as a cloud of gas, existing in three-dimensional space. When we look at how this field changes, we see two distinct types of movement. The first is a linear shift, where every part of the field moves in a straight line toward a specific point, much like arrows pointing directly to the center of a cloud. The second type of movement is a vortex or swirl. By combining a point's position in space with its directional change, we create an action that forces the field to move in circles around an axis. This rotation acts like a lever arm. The turning effect is non-existent at the very center but becomes increasingly powerful the further you move away from the origin. These visual flows represent the instantaneous rate of change within the field. The mathematical logic behind these movements relies on a specific identity that balances these interactions. When we try to calculate the effect of applying this turning action twice in a row, we engage in a complex logical expansion. The proof of this identity functions as a balancing act of symmetries. By analyzing how different directions interact, many potential outcomes cancel each other out because the directions are perfectly mirrored or because the order of certain operations can be swapped without change. Ultimately, this logical process proves a specific consistency. Applying this combined rotation action upon itself results in a single, negative version of that same rotation. This mathematical identity serves as the bridge between the predictable world of classical mechanics and the probabilistic world of quantum mechanics. In classical physics, angular momentum is simply a product of where an object is and how it is moving. In the quantum realm, however, we replace physical momentum with an operator, a rule that describes how a field changes across space. A vital distinction in this quantum world is that the order of operations matters. In basic algebra, multiplying a value by itself in a cross product results in zero. However, because these spatial operators do not commute, meaning doing a then b is different from doing b then a, the cross product of the rotation operator with itself is not zero. This non-zero result is the very foundation of how we describe the behavior of subatomic particles. Finally, these concepts reveal deep truths about the symmetries of our universe. A simple directional change is the generator of translation, meaning it is the rule that allows things to slide forward, backward, or sideways in space. The combination of position and change, however, is the generator of rotation, allowing things to turn. The fact that the rate of change of the rotation is proportional to the rotation itself proves that three-dimensional rotations are non-abelian. This means that the orientation of an object depends entirely on the sequence of turns it took to get there. Whether visualizing a swirling cloud or calculating the path of an electron, this identity confirms that the geometry of our space is fundamentally defined by how these rotations interact with one another.